our next and last invited speaker in this symposium is Thore Graepel from DeepMind. And yeah, I think many people will know Thore, so I decided to keep it relatively short. So Thore is leading one of the DeepMind research teams, focusing particularly on multi-agent learning. At the same time, he's also still affiliated with UCL as a chair of machine learning. Thore is around already for some time. He obtained his PhD 2001, I believe, I read, from the University of Berlin. Did some postdocs and then I joined Microsoft Research in Cambridge in 2003. And he spent some time there. He co-founded the online services and advertising group, which, as you can imagine, is an important topic that has kicked off maybe since the early 2000s. And then he at some point joined DeepMind, and he has been doing incredibly cool work that I'm quite certain many of you will have seen. The list was way too long to mention everything, but you know, some of the things that I particularly like is multi-agent reinforcement learning and sequential social dilemmas. We're already touching upon the importance of those in the break. Value decomposition networks, and of course the work on AlphaGo and MuZero that I believe he will be talking about more. So I can understand that not everybody can welcome Thore as we would like, so I will do it for you. Thore, welcome. The screen is yours.
Great, thank you very much for the kind introduction, Franz. In general, I'd like to thank you, Franz, Chris, Shogi, and Carl for organizing COMARL this year and creating such a wonderful forum for all of us to get together. It's not quite as in person as we would have liked it to be, of course, but still very nice. And I think we're doing a good job as a community to come together despite the difficulties of the virus situation. Yeah, I have the privilege of talking about some of my favorite work. Namely, I'm planning to tell you about the story of AlphaGo, of AlphaZero, up to our latest work, MuZero. And this is work at DeepMind with a number of amazing people. In fact, I've been blessed by all the fantastic people that I had the privilege of working with, and most of the credit needs to go to them. And I've, of course, put the relevant citations with many of the people into the presentation. So let's look at the plan. So I'll start off talking about AlphaGo, which of course was the first program to defeat a professional Go player at their game. I'll then move on to describe AlphaZero, which was a generalization of AlphaGo to more different games, but also using less human knowledge. So in 2 dimensions, we were trying to make things more general by taking a number of domains and also using less specific human-infused knowledge there. And then finally, I'll talk about MuZero, which extended the domains that it works on even further, now including these video games in the Atari suite. But we also designed it such that you now don't even need to enter the rules of the game, but it can also learn the rules of the game from observation. A notion that in reinforcement learning, of course, is referred to as model-based reinforcement learning, where you need to learn the dynamics and the rewards of the dynamic of the environment by interacting with it. So let's start with the AlphaGo journey. And here, of course, people like David Silva, Aja Huang, Chris Madison, and many others contributed to this work. And you can find the paper online. And I don't know if any of you played the game of Go. I'm a huge fan of the game of Go. And, you know, it's one of the oldest board games in existence Back in China, it was one of the 4 things that one needed to master next to poetry and calligraphy. One of those arts that anyone who wanted to be taken seriously needed to master. It still is a hugely popular game, of course, with over 40 million players worldwide, and an enormous complexity that I'll talk more about in a little bit. So the complexity of the game arises because in any given position, there's approximately 200 different moves one could make. And the game also lasts approximately 200 moves. And so you can imagine that that's an enormous game tree that is spanned by these possibilities. And, people have been saying as a comparison that there are as many Go positions as there are atoms in the known universe. But the truth is that if there was for every atom in the known universe another universe, then there would even be more positions than atoms in that collection of universes. It's of course, we know these combinatorial spaces are incredibly rich. And so that was really the main challenge for finding an algorithm that could play this game well, together with the fact that it's really hard to design an evaluation function for the game, because it's not so clear for a given Go position who will more likely win, black or white. And for a long time, that was an open question. Now, the way we addressed this problem was by introducing 2 types of neural networks that can manage the size of the search space. And the first one is the policy network. And it takes a position, a Go position in this case, and predicts good moves that professionals would make in a given position. And you can see that really it is just a classification problem, because the data it is trained on is as input a Go position in some vector-based representation. And the output is one of 361 possible moves, because that's how many vertices there are on the board, and that's the maximum number of moves that are available in any given position. And so really training this system is a classification problem, and so it's a move classifier that can give us a probability distribution over professional moves. The second neural network that we trained was a value network, which predicts the value of a given position, say from the perspective of black. So it takes the position and it predicts the probability that black will win in that particular position. And again, you can think of this as a classification problem with a probabilistic output, something like logistic regression, because the data set that you would train it on would be pairs of positions and the outcome of the game, which is pretty much binary, win or loss. So again, a relatively straightforward machine learning problem as seen in isolation. So then in AlphaGo, we started with a supervised learning approach, which is always the best thing if one can do it, because we know relatively well how to train neural networks now at large scales. Reinforcement learning, multi-agent, and so on always brings complications, but we can do imitation or supervised learning relatively easily. And fortunately, we had a large set of human expert positions available, because people had been collecting Go games online for many years. And so there were hundreds of thousands of those available. And of course, we only wanted to train on strong Go games so that we could harvest the strong moves. So first step, we train the policy network. And as I said, it's basically a classification problem. We have a data set of positions. We know which moves was made in those positions, and we can train this policy network. Once we have such a policy network, we now have a way of generating more Go games, because this policy network can now play against itself. And it can do so at a very high rate. And so it can produce a ton of new Go games just by playing against itself. And now that we can generate a very large data set of Go games, we can now train the value network, because now we can sample the positions of these newly generated Go games, can take a position, we can look up how that game ended, which will be black win or white win. and we can train the value network based on that to be able to predict for a given Go position whose position is better, blacks or whites. And we get a probability output for that, of course. And then we can take the policy network and the value network and put them into a Monte Carlo tree search, and the resulting system is effectively how AlphaGo works. Just to imagine how the two neural networks operate in this huge search tree, you can think of this cartoon of a search tree here, and the role of the policy network is to make it narrower, because it allows us to focus on just a small subset of the moves that are available in any given position. So that's what the policy network does. Here it's just one move it focuses on, because of course it focuses on more than one move in any given position. But that's the idea, narrowing it down. But then the other network, the value network, allows us to shorten the search, because if we look at just outcomes, of course, the game result is only available after 200 or 300 moves, but we would like to stop the search short earlier. And that's what the value network allows us to do. It provides an empirical evaluation function such that at limited depth of the search tree in intermediate positions and not in terminal positions, we can evaluate the value of the position and then propagate that up the tree as normal in Monte Carlo tree search. So we wanted to test this, and we went through a lengthy pipeline of testing against old versions, testing against a pro player, Van Hui, and eventually ending up with doing a test match against the strongest player of Go at the time, Yi Sedol, who was the winner of 18 world titles, a 9-dan professional player. And in 2016, this match was played. Maybe some of you were able to follow it. I just want to give you a little spirit of how that was for us, because it was an incredibly exciting match. And a documentary film was made about it, which is available on YouTube, called AlphaGo. And I'd recommend you to view it if you're interested in that kind of thing. But let's take a look at the trailer just to get a flavor for what this was like back then. I'll just mute myself so that you can hear the sound.
Go is the world's oldest continuously played board game. It is one of the simplest and also most abstract.
Beating a professional player at Go is a long-standing challenge of artificial intelligence.
Everything we've ever tried in AI just falls over when you try the game of Go.
The number of possible configurations of the board is more than the number of atoms in the universe.
AlphaGo found a way to learn how to play Go.
So far, AlphaGo has beaten every challenge we've given it, but we won't know its true strength until we play somebody who is at the top of the world, like Yi Sedol.
A match like no other is about to get underway in South Korea.
They said all is to Go what Roger Federer is to tennis.
Just the very thought of a machine playing a human is inherently intriguing.
The place is a madhouse.
Welcome to the DeepMind Challenge. The whole world is watching. Can Yi Sedol find AlphaGo's weakness? Whoa. Is there, in fact, a weakness?
The game kind of turned on its axis.
Look at his face.
That is not a confident face.
It's developing into a very, very dangerous fight.
Ooh, hold the phone. Lee has left the room.
In the end, it is about pride.
I think something went wrong.
Yeah, it's made a mistake.
He's got to pronounce America.
These ideas that are driving AlphaGo are going to drive our future.
This is it, folks.
So I hope that gave you a flavor of the excitement that we had in this match in Korea. And I will spoil the outcome. I probably already know it. AlphaGo won the match, in fact, 4-1. It was incredibly close in many ways, because, Yi Sedol coming back with that one victory really made us question a lot of things about the system and so on, and led to further developments. But in the end, the system won out, and Go players across the world, of course, were very excited, and now these types of systems inform a lot of how Go is being played, and has instilled the game and the player community with new ideas of how to tackle the game, and what good Go playing actually looks like. I want to give you a little example of a move that we found particularly amazing, because AlphaGo came up with a move that nobody quite expected, and I'll show you the scene here when our two commentators first discovered that AlphaGo made this famous move 37, as it became to be known, and T-shirts were printed with move 37 on it, and tea mugs and so on, which was quite fun for us. And so here is what that looked like when the two commentators encountered the move.
About is this kind of evaluation value?
That's a very surprising move.
I thought it was a mistake.
So they thought it was a mistake. And that shows you how the system was already to some degree transcending the ways in which humans think about this game, because the move violated a very basic strategic rule of Go that people tend to adhere to, namely not making shoulder moves towards high opponent stones. And AlphaGo in that particular context judged that the move would be correct despite this unwritten rule, and it turned out to be a good move in this context indeed. Good. Let's move on to AlphaZero. Spurred on by the success of AlphaGo, we wanted to generalize the idea of the algorithm. And there were really two directions here. One was, can we tackle more than the game of Go? Does this hold for other games? And we restricted this to these two-player zero-sum board games, and tackled the games of chess and Shogi as well. But the other idea was, can we do learning from first principles? So we wanted to use no human data and have the system learn solely by self-play reinforcement learning, starting from random. We wanted to design the system such that it doesn't use human features and only takes raw board as input. In AlphaGo, there were still some board features that we had designed that we knew were helpful for the learning process. And we wanted to take that away here. And effectively, the only prior knowledge that comes in here now is what I like to call the Kantian notions of space and time, because space comes in because we do use convolutional neural networks for representation learning, and time comes in because, of course, the temporal structure of move following move is still present, and of course made use of heavily in the system here. So let's take a look at what that looks like now. First of all, we need to generate data. So we have a randomly initialized system now. It again has a policy network and a value network, and it uses Monte Carlo tree search. But initially, the policy and the value network are randomly initiated, and we generate data with that. Of course, that's not very strong Go that's being played at this point, but it is enough for the value network to pick up on what are good positions and what are bad positions, because eventually even those random games come to an outcome, and that outcome tells us something about the value that earlier positions in that game had because of the continuity of the value function. And so the system has something to go on and can improve a little bit. And that amplified through the tree search leads to stronger play, which can then be picked up by training the policy and the value network, and then the iteration takes off and the system becomes stronger. So here, quite clearly, the system takes a position, makes a move, that creates a new position, it acts on that new position, makes a move, and so on. It plays against itself up to a terminal position when we know who won. Then on this data, reinforcement learning kicks in. And so we train the new policy network. And it really just predicts the moves that AlphaZero is going to make. But of course, AlphaZero has the search tree. So we now train the policy network to imitate what the full AlphaZero system, including the old policy network, the old value network, and the tree do, and predict what move it would come up with and find that directly, so to speak, through the policy network by imitation. Because we have these self-play generated games, we take pairs of positions and the move made by AlphaZero or by the previous version of AlphaZero, and we train a classifier on that as before. Similarly, we can train the new value network, V prime, which predicts the winner of a given position. We have these self-play games now. We know their outcome. We can pick a position in between. We have the outcome of that game. We can do the logistic regression or training the value network in order to predict how good that position is. So now we have a new policy network P prime and a new value network V prime, and we can put them back into the tree search and generate new data through self-play. And the resulting system, of course, is stronger now because the policy network is stronger and the value network is stronger because they've been trained on better data from the previous iteration. And that's really the iteration we're running that leads to stronger and stronger play. So how did this work? First, in the game of Go, it took about 8 hours of training until this AlphaZero system beat the old AlphaGo system, and it continued to improve from there. And after a few more hours, it wins 100-0 against the old AlphaGo system. So what is interesting here is that somehow AlphaZero is unshackled from the way humans play. AlphaGo was still, in some sense, constrained by the features we gave it, in addition to the raw board, by the initial training on human data. It had a particularly human style, actually, that people recognized. Whereas AlphaZero was now free of all of these shackles and could really just optimize in self-play how to play this game well. And it went far beyond the original AlphaGo. What I find particularly fascinating is that this process was able to discover new knowledge and old knowledge, actually. So in order to understand what's going on, you need to understand that in Go, there are certain corner patterns that we call joseki. And these are certain sequences that can be played in corners that have been cultivated for hundreds, sometimes thousands of years, that humans have improved upon slowly, that they memorize when they start playing, and that they are some kind of local tactical wisdom of the game. And there are many books about these, and I studied many of them myself when I learned Go. And what you see here is a timeline of what types of opening patterns AlphaZero played. And the interesting thing is it discovers many known patterns that humans also play, but it also discards some again. For example, this particular one, which is actually quite well known, joseki, you can see here that on the plot on the right, on the x-axis is the hours of training, and on the y-axis how often it plays that particular pattern. And so after 30 hours, it starts playing that pattern and gets really excited about it for a while. But then, by 70 hours, it has found countermeasures against it and is not using it anymore. And so a pattern that was long held by humans has been discarded by the system purely by analyzing the space of strategies through self-play. And now, of course, many newly discovered josekis that it does play are also taken up by professional players. So there's an exchange between the human community of players and AlphaZero or publicly available versions of it now. Good, so much for Go. But of course, we were excited to also apply the same methodology to chess because, in many ways, that's a more approachable game for many of us in the West. And of course, computer chess is one of the most studied domains in history of AI. It has been studied by Babbage, by Turing, by Shannon, by von Neumann, and it's generally considered to be a Drosophila of artificial intelligence in many ways. And we know, of course, that chess computers are already pretty good. Deep Blue defeated Kasparov in 1997, and systems now, even though it may have been tight in 1997, are indisputably considered superhuman. They are considered enormously strong, and human players generally don't stand a chance against them now. There's also the game of Shogi, Japanese chess, which is even more complex than Western chess. The board is larger, and there's also a larger action space. For example, in Shogi, if you capture a piece of the opponent, you can put it back into your own army as a move. And that, of course, makes the game more complex. And in the game of Shogi, human world champion level was only achieved relatively recently. So what these traditional chess and gameplay systems have in common, of course, is that they usually operate on a handcrafted evaluation function that has been optimized by humans, and that it uses alpha-beta search and related methods to be very efficient at searching the game tree. And also there are many additional heuristics that are being used to make these programs better and better. Just as a little view on that, and I don't know all the techniques listed here, but these are all the heuristics used in the state-of-the-art chess engine Stockfish, which is very, very strong. And you can see here all kinds of board representation hacks, search hacks, transposition tables, move ordering heuristics, tricks on the evaluation function, and finally even endgame table bases. So for endgames with very few pieces, the optimal play is known and has been pre-calculated, and the system uses these things. And in contrast, AlphaZero, of course, uses none of that and just uses the technology that I just described to you previously. But often, of course, progress comes when we can simplify our thinking about things. And I think this is a beautiful example of that. So how did AlphaZero fare here? The graph below shows the situation in Go and how it went past AlphaGo and became better and better. Then in chess in the top left, you can see that it surpassed Stockfish after 4 hours of training. Now those were a lot of games, of course, and we had a very efficient parallelized pipeline. So that's how those times come about. And in Shogi, similarly, there was a state-of-the-art program called Elmo that used with alpha-beta search and a heuristic evaluation function, and AlphaZero surpassed that also after a couple of hours. So that worked very, very well. One thing that I found even more interesting than absolute performance, though, was the fact that it used by a great factor fewer node visits than, for example, Stockfish. So you can imagine that a modern traditional search in a chess engine searches tens of millions of positions per move. So it visits those positions and evaluates them effectively. And in contrast, AlphaZero searches fewer positions by a factor of 1,000 and only searches tens of thousands of positions for a given move. And it does that, of course, because it selects the moves that it does search in a smarter way using the policy network, which narrows the search in a smart way. But we need to keep in mind that a human grandmaster searches even fewer positions than that, again, probably by a factor of 100 when they make their decisions. So somehow, of course, human decision-making taps even more deeply into intuition and some kind of holistic understanding of positions than AlphaZero does. But, you know, it gets us some of the way there, and I thought that was an interesting observation to share here. I'd also like to show, for those of you who do play chess, one position that I found particularly remarkable, and they already call it the immortal Zugzwang game on YouTube, where this game has been commented. So here, AlphaZero plays white, and Stockfish, that is this state-of-the-art, very strong chess engine, played black. And the game has entered a situation which we refer to with the German word Zugzwang, because there is literally no black piece that black can move when it's their turn now, that doesn't lead to a deterioration of their position and eventual loss. We can go through the pieces, and if you play chess, you'll see that moving any of these pieces is either impossible or leads to a catastrophic loss. The pawns, of course, get lost when they are moved forward. And of course, in particular, the pawn on f7 is heavily attacked 3 times by white. And so that binds most of the forces. And of course, you can see the black queen in the corner is in a desperate position and cannot enter the game at all. And Stockfish at some point decides to sacrifice it against the rook, the white rook, just to get some maneuvering out of it. But of course, with that disadvantage in material, Stockfish stands no chance. So people have commented on AlphaZero's style, and many grandmasters have agreed that it plays a beautiful and very aggressive kind of style, not at all like traditional computers, but more with a view on developing the dynamics of the positions, how it can deploy its material rather than just trying to collect pieces, so to speak. Good. Of course, these are all games, but we were very happy to see that researchers picked up on the methodology of AlphaZero to pursue applications in a number of useful domains. And here are 2 examples. Ziegler et al. In Nature 2018 devised a system that helps to find ways of synthesizing organics chemicals. You can imagine that certain synthesis steps are known. You know, there's a huge database of certain processes that are well controlled and that people can run. And now the question is, how can you arrive at a particular target that you want to synthesize? And you can see that that also looks like an inverted game tree, and that, again, it would benefit from the 2 things that a value and the policy network provide. The policy network says which kind of synthesis should be tried next, so to speak. And the value network says, you know, how much closer does that get us to the target that we want to synthesize? Similarly, there's an application for the control of quantum systems by Dalgaard et al. And here the optimization is to drive the quantum system to a particular state by devising a certain well-designed sequence of energy pulses to it. And that, you can see here the energy pulses on the bottom left, and that composing that sequence of energy pulses to drive the system towards that state is the search problem that, again, can be formulated as a tree search problem and solved in a way very similar to AlphaZero. Let's finally move to MuZero, the idea of planning like in AlphaZero, but with a learned model where the rules of the game are not given. And we tried that out not only in chess, shogi, and Go, but added the domain of Atari games, you know, the famous 57 Atari games that became such a fascinating domain in 2013, I think, and where deep reinforcement learning had some of its initial successes. And this is joint work with Julian Schrittwieser, Thomas Hubert, Yannis Antonoglou, and Dave Silver, and others. So what was the idea here? The idea was, can we build a system that makes predictions that help it to plan using its research, but only predict the things that it actually needs to do that planning. If you think about it, traditional model-based reinforcement learning algorithms often try to recreate in their model the observations of the state. You know, for example, in Atari games, to predict what would happen if I do this in terms of what you see on the screen, you know, with Pac-Man moving to the right or the ghosts moving in some direction or whatever it is in that game. But we take a different view here and we say that doesn't actually matter for the planning. And what matters is really only a set of functions that we need to describe the MDP and to do the planning. And I show you now what that looks like. Namely, we really only need predictors for the policy, the value, the reward, and the next state. So let's take a look at this. We have a Go position or any game position or state that we want to look at in the real world out there, say a Go position in this case. And so what we first have in the process is a function h that maps this representation in the real world, which could be a pixel image or a chess or Go position, into a vector-valued latent representation that we call S here. So that is the initial state, and we map it into this vector-based representation. From this vector-based representation, we can calculate the policy and the value as we've done before. Just now, we calculate it on this latent state representation rather than on the observations of the state directly. And finally, we calculate the dynamics, namely essentially what we would have to know from the MDP to solve it. So given a previous state, sk-1, and the action taken at step k, this function gives us the predicted reward at that point when we do that, and it gives us the next state. But the next state in that latent representation. Once we're in the latent representation, we never need to go back to the real world. So of course we can iterate this now, because now we're in state 1, S1 here. And from here, after we've done the predictions of policy and value for that, we can now apply an action to it. And the state and the action together, of course, allow us to application of the function g, which predicts what the next reward and the next state will be. And from that, we can again calculate the predictions for policy and value. And all of this rollout in the Monte Carlo tree search now happens in this latent space, and we never need to leave that latent space again. We can do everything in that latent space. H is our way of getting into it. F is our way of making predictions from those latent states, and G is our way of rolling forward the latent state and predicting the reward that the environment will give us. So that's really the key idea here. Now let's take a look at how we generate self-play data from this. Again, we start with a state, of course. We apply the Monte Carlo tree search. It gives us a distribution over moves that we would make at the root. And we sample an action from that, and that allows us we submit that to the environment. The environment runs forward, gives us the next state, and we can again do the hypothetical planning, get a move, and so on and so forth. Of course, the system does assume that we have interactive access to the environment. So you can play a move and it will tell you what's happening. And of course, through that, we can learn what the dynamics of that environment are. But within the tree search, all the rollouts happen in that latent space. So we're not drawing on the environment for actual hypotheticals. It's a bit like, you know, when you first start to play chess or Go, you tend to try out certain move sequences on the board. Whereas when you're more advanced, you do that in your head. Well, this system does it in its head, and it doesn't do it on the board. It doesn't use the simulator for making those hypothetical moves for the tree search. Then, of course, we need to understand how the model is learned and updated. And so we've now created self-play data as before, as in AlphaZero. We have a pool of self-play data, and we can now pick a trajectory, pick a point in the trajectory, and roll the model forward from then on, where we take the actions of that real trajectory to drive the model. So what that gives us are states that are aligned with how the actual move drive the real environment forward, or drove the real environment forward when the game was played. And now we get all the quantities that we need to update the model, because we see for the action what was the next state, and we can update our dynamics model. We observe what reward happens. We can update our reward model. And of course, we can also update the policy and the value networks, because we know the outcomes of those games and we know which moves had been made. So that's really all that's needed. Here are the three things again. On the left, you see the functions that H gets us into that state. G is the dynamics. F are the predictions. We know how to then generate trajectories in interaction with the real environment. And then we can draw on those trajectories to learn our model that allows us to, at the same time, model the environment and play well in it. So we talked a lot about Shogi.
Quick update. You have now 15 minutes left, including the question time.
Ah, yeah, wonderful. Thank you. So you see here some results for the Atari games, because that was the new set of results here. And the MuZero system in the top half, you see here, has higher scores than the previously best system, which was R2D2, by using fewer environment frames and less training time. But we also looked at a version of MuZero that we call reanalyze, which does not always generate new trajectories, but can use old trajectories and reanalyze them in light of the updated neural network models. So it goes back over old data and learns from that. And that then leads to even greater improvements over the existing model-free methods that are listed here at only 200 million environment frames. So the system can deal with scarce data, if you like. 200 million isn't really scarce data, but we're trying to push down the amount of environment interactions that it needs, of course, to achieve its performance. The system worked very well in chess and shogi and met the AlphaZero performance. In Go, it even went a little bit beyond the AlphaZero performance. And we think that's probably because it can somehow cache within its recursive representation learning, when it rolls that forward, interesting computations about the position, and thereby gets even more capacity out of those neural networks. But it's a bit of an open question. But what you see on the right here is the evolution of how well it does on these Atari games, 57 Atari games. The top blue line is the system's mean performance, and the bottom line with dashed line is the median performance of the system. And the horizontal orange lines are the previous state-of-the-art system, R2D2 here. One interesting question that we wanted to address was, how does the system scale? And here, the idea is that the system was trained really with only a few steps into the future, I think roughly 5 steps. But it turns out that it can, you can scale up the search time in the Monte Carlo tree search so that it goes much deeper than 5 into the tree, and it still works. So the 5 steps training was sufficient to create a forward rolling model that was still useful far further down in the search tree, which is an important property because that's really what makes the system stronger, if it can plan more deeply, even beyond the horizon on which it was trained. Finally, I'd like to point out that the system could be trained at with different amounts of tree search. And here we have ranges from training it on just 5 simulations into the future, up to 50 simulations into the future, which is how it has been tested here. And you can see here that, of course, if you train it with 50 simulations into the future, that's the fastest thing you can do. You extract the most information out of it. But even if you train it with, say, 7 or 10 simulations, which are the lines in the middle here, it still learns pretty quickly, and also still performs well, even if you use it at that level. So a few steps of Monte Carlo tree search during the training already help it do well during testing at 50 steps. And finally, we also compared to Q-learning in our system. That's the plot on the right here. And the system just learns much faster than normal Q-learning does within our training pipeline. And I include this here to make sure that you see the comparison is fair. We implemented Q-learning here exactly with our neural networks that we also used for MuZero. And it's really just the advantage of the model-based approach that drives the much faster learning at the beginning here, and also the higher performance at the end. Good. Let me conclude. AlphaGo, of course, now almost an oldie, a powerful combination of neural networks and Monte Carlo tree search that can help us in these 2-player zero-sum board games. Then AlphaZero, a more general approach that did away with a lot of need for human intervention, human features, human knowledge, and was able to generate new knowledge, new ways of playing these exciting board games. And then finally, MuZero, a model-based RL approach that adds even more generality because you can potentially use it in the domains where you don't know the rules of the game. It is good at data efficiency, and it now also works in single-player domains. You may have noticed I didn't mention this, but of course, Atari is a single-player domain. But then, of course, a system that works in single-player domains can also work in multiplayer domains if you then train these systems independently against each other. Still, of course, there are many open problems. The dynamics here is assumed to be deterministic. So, of course, it will be interesting to see what happens with stochastic environments, for example, like backgammon, where the branching not only happens based on your decision, but also on how the dice throw comes out. In another interesting question, how to deal with imperfect information and mixed strategies, as would be required in poker. What happens if the action spaces become really large and combinatorial, like in a game of diplomacy? That certainly has open questions. And then, of course, we're really excited about potential real-world applications, because now that there is no need to know the rules of the game or the dynamics in advance, there should be many more domains where this type of approach could be useful. Great. Thank you very much.
Thank you, Thore. Great talk. So we have time. We have actually plenty of time to go over some questions. So please do not hold back. Feel free to.
Maybe I'll ask a question to get us started, I guess.
Yep.
So in terms of imperfect information games, it seems like since you're learning a latent model, then a lot of the stuff would transfer, right? Because once you learn a latent model, you can just operate in the latent model, even if your actual domain is partially observable. And I guess in some sense, Atari, if you don't cheat and use 4 frames, is partially observable as well. But I don't know if which representation you use there. So thoughts about that would be interesting to hear.
Yeah, I think partial observability is in a way something that the system could deal with. I was here referring also to imperfect information in the sense that you might have to employ a mixed strategy to avoid being predictable. And in those types of situations, I think you would need to come up with a different way of dealing with this. It's an interesting set of questions, regret matching and things, regret-based learning, things like that could maybe be fused with this approach somehow in order to enable that. Yeah.
But you think partially observable environments, then you wouldn't have to do anything else for the method. You could directly apply it in partially observable environments. Is that the answer there?
So I agree with your assessment that, in some sense, we did the Atari four-frame repeat. And so in some sense, it is a bit like that. But I think if it gets too strong, then I think in the prediction of the dynamics, there could be bifurcations caused a bit like the stochastic case, because if you just don't know, then it looks a bit like stochasticity. And so then you might need multimodality in the predictions that you make of what the next state is. And so that we currently haven't paid any attention to. But I think that would be a super interesting direction for future work, to see how one could make a distributional prediction and how to handle that. Because that then also interacts with the tree search, of course, and maybe Monte Carlo could handle it by going down the path with the right kind of probability distribution, but we really haven't tried that.
Yeah, cool. Thanks a lot.
So I see that there also was in the chat a question that I now noticed by Ruben, but that appears to have been answered. Ruben, is that correct? Is Ruben still here? And otherwise, we have a question by Clement.
Yeah, I can ask it live maybe. Thank you for the great talk. I was just wondering in MuZero regarding the latent space. Well, first, what is the dimensionality of the latent space? But more importantly, do you have methods that can help you understand what is actually encoded in the latent space? For example, in Atari game, it would be interesting to know, for example, if some relevant entities are encoded in some forms, for example, the objects or the enemies or the walls in the game. And so are you aware of methods to figure this out, or are you developing some new methods to go into the direction?
Yeah, that is a great question. So I mean, the latent space is somewhere in the thousands, 2,000, maybe 4,000, and the truth is we've left it mostly completely in the unknown. It would be a super interesting question what it actually encodes. And you can only imagine it needs to for a game like chess, it somehow needs to carry all the relational information of the board, right? How else could it be doing reasonable planning? So it needs to be somewhere in there. And there have been attempts at trying to couple it back to the real representation. You could, for example, try to reconstruct the next state based on your latent representation. Speculating that somehow the information needs to be in there, and you can recover it. And we tried to do that, and in fact wanted to use that to make the system even more data efficient, because if there would be an additional reconstruction loss for the original state, you could imagine that constrains the learning system more, and thereby you could maybe use less data to learn those representations. But we haven't been able to make that work. But I've seen some other groups who have played with it, and some other groups have been able to make it work. But if you had any ideas of how one could investigate this latent space, that would be quite interesting. Maybe representation or something of chess positions some low dimensionality embedding and things like that could be used, I guess.
Yeah, or some receptive field analysis maybe that like it is done in vision as well, or things like this might be maybe interesting in this direction. Okay, thank you very much.
Thanks.
Any further questions? Not, I can ask one more follow-up question to this, I suppose. So there's also a bunch of work in model-based reinforcement learning, which tries to build on these notions of bisimilarity and bisimilarity metrics, or a different term that people use is MDP homomorphisms. So here in this work, it seems that rather than trying to learn such a model which kind of adheres to those metrics, so essentially they say, well, a latent state representation needs to do two things. You need to be able to predict the reward and to predict the next latent state, right? Here, rather than doing that type of optimization, you additionally also include this policy and value loss in the objective. So what is the effect? I guess what are the pros and cons between those two types of approaches? Do you have an idea about that?
Yeah, so you're characterizing that right. So we call this the underlying principle, if you like, the value equivalence principle. The idea being that we do create an MDP in some sense in this abstract space, where the only condition that we're trying to enforce is that it's value equivalent to the real MDP, in the sense that if you roll the model forward within that latent space and look at the resulting value function or rewards that it gives you, that it gives an equivalent result, that being the minimal condition that you need for it to be useful in planning. I think one thing that that makes this approach a little less useful than general model-based methods, like the ones you're mentioning, is that the reward is baked into the representation here. So people often argue that one advantage of model-based reinforcement learning is that you can learn about the world, and then if someone gives you a new reward function, you would pretty instantly be able to find a good policy for that reward function, because you've already learned the dynamics and now you have the new reward function, and you just need to, do your dynamic programming magic, so to speak, and you're done, right? And that doesn't quite hold here, because we're baking into the representation reward-related quantities, in particular the value function predictor, the policy, and the direct reward prediction itself. And so the representation that we learn isn't actually reward universal. And I think that is maybe the main difference from these other model-based RL methods. And that would be an interesting thing to disentangle. Would it be possible to build a system a bit like this, but which would preserve the reward independence of the representation that's been built? And, could we just somehow swap out reward or learn the reward separately of a given environment and draw on the dynamics remaining the same? If you suddenly played a different game of chess, but the pieces moved in the same way or something like that. So I think that would be super interesting, because it would come even closer to the dream of model-based RL, that we can just explore the world, learn about it, and then afterwards optimize any reward function within it that we like.
Yeah, to be true, I think those other methods are certainly the things that I worked on. They are not reward independent either, but I agree that's a very interesting future direction. So cool. All right. Yeah, unless there's a last question. Anybody else? Last call. In that case, I suggest we thank Thore again for a great talk. Thanks, Thore.
Thank you very much.